Hello everyone, my name is Mareike Grotheer and I am a junior group leader at the Philipps University in Marburg. In this course, we'll go over a special use case of tractometry, which is to apply it to infant data. I will start with a short motivation, and then for the rest of the course, I will slowly build up an example tractometry pipeline. I will begin with an adult pipeline and then tweak it for infant data, and then we will wrap up. Throughout the talk, some of my slides will have little teal boxes, such as the one here on the right. These are not immediately relevant to the talk, but rather point at resources for further reading and other hopefully useful links and tips. During the course, I will also pose a few quiz questions, and I would be thrilled if you would all participate in the quiz. So then let's dive right in. First of all, what is tractometry? This you have heard many times already today, but it can't hurt to have a brief repetition. The term tractometry describes an approach where first you would identify the large white matter bundles or highways in an individual's brain. As for example, the arcuate vesicles that was identified here in the brain of a newborn. After identifying the bundle, you would then quantify its microstructural properties. You can use any microstructural measure, such as fractional anisotropy, mean diffusivity, or, as in this example, quantitative R1. Critically, in tractometry, you would evaluate the measure of interest at multiple steps along the length of the bundle. So rather than getting a single mean value per bundle, you get an idea of how the measure of interest changes at different locations in the brain. For this reason, tractometry is also sometimes referred to as a long-tracked analysis, and the resulting graphic is often called a bundle profile. And once you have such a bundle profile, you can start asking really interesting questions. For instance, you can ask how the bundle profile changes when an infant gets older. Importantly, you can perform tractometry on all sorts of human and animal diffusion data. Today, I'm hoping to convince you that doing tractometry in infant data is particularly exciting. For starters, this is because the human brain changes most rapidly during infancy. In the first year of life, the white matter volume has been shown to increase by about 11%, and most of the white matter myelin growth happens in the first year of life as well. Moreover, many psychological and neurological disorders already emerge in infancy, and a better understanding of their emergence early on may promote early interventions as well. Further, there are specific issues that emerge in infancy, including the negative consequences of preterm birth or fetal alcohol syndrome. More broadly, there's just not that much known yet about the white matter development in the living infant brain, so there are still many open questions to tackle. And the best part is that you do not necessarily need to be equipped to collect infant data yourself, as there are large-scale open data sets that include infant diffusion data. And I'm listing a few examples here in the blue box. The most prominent example is probably the data from the Developing Human Connectome project, which includes hundreds of infants. So just to drive home how new tractometry in infant really is, here's our first quiz. If a PubMed search with diffusion and bundle in adult gives 1,500 results, what do you think? How many results do you expect for diffusion and bundle in infants? 50 results, 150 results, 500 results, or 1,000 results? I hope you had a chance to pick your answer. The correct answer in this case is 150 results. So just to illustrate what kinds of questions you can ask when applying tractometry to infants, here are a few examples. In the first example, Wilson and colleagues were recently able to identify white matter bundles in utero before the infants were even born, and then describe the bundle development in utero as well. Further, Dabner and al. Showed that white matter microstructure measured at birth in infants born preterm relates to their two-year language outcome, which I think is pretty exciting. Finally, in my most recent study, we found that white matter myelinates faster in utero than ex utero, and that this difference in myelination rate can explain the delayed myelin growth seen in infants born preterm. This is by no means an all-inclusive list, and there's much more exciting research out there, but I hope that these examples could pique your interest. Okay, so now let's dive into our example tractometry pipeline. There's various different toolboxes and approaches that we could use, but this would probably be a pretty typical modern pipeline for adult data. We're going to go over each step in detail, but overall, you would first pre-process the diffusion data, then you would generate fiber orientation density functions, or FODs, and once you have those, you can generate a whole brain connectome, which you can then delineate into individual bundles. And finally, you can plot your microstructure measure of interest along the length of the bundle. The first step in the pipeline is to pre-process the raw diffusion data. At the very least, this would typically include correcting for susceptibility-induced distortion, eddy current correction, and motion correction. Out of these processing steps, motion correction is one that is particularly challenging in infant data. After all, we cannot ask an infant to please lie still in the scanner. Moreover, since our infant brain is smaller, the same amount of movement will be more detrimental to data quality. When it comes to motion, the best way to go is to prevent it from the get-go, so at the time of data collection. And even though we can ask the infant to please lie still, there's still many little steps that we can do to substantially decrease the infant's motion. First, you would typically want the infant to be naturally sleeping during the scan. And to promote this, it is helpful to scan at night during the infant's natural bedtime. It is also helpful to feed the infant right before the scan, as this also promotes natural sleep. You can further reduce motion and encourage sleep by swaddling the infant, or even by using a professional immobilizer. There are now also infant head cards on the market that closely fit the infant's head and will likely have a large impact on data quality. These cards also have space for headphones and other ear protection, which of course is not only vital to the infant's sleep quality, but also for their well-being. Finally, and most importantly, you would need to monitor the infant carefully and be very patient. If the infant wakes up or moves too much, it's probably best to start the scan over. But all that said, as with all MRI scans, there will always be some motion left over. So when working with infant data, you just want to make sure that you're utilizing the latest approaches for motion correction. For example, you could use the newest version of FSL's eddy tool, which performs motion correction in 2 steps. First, it is outlier replacement, which means that every slice whose average intensity is some standard deviation lower than the expected intensity is being replaced by a predicted slice. The idea behind this is that motion will lead to signal dropout in the diffusion image, and in order to get rid of this, eddy removes slices that have very low signal. In the next step, it then checks if slices within one volume are aligned to each other, and if not, it realigns them using a process similar to rigid body alignment. I would also recommend paying attention to the output of your motion correction, as this will help you decide if some data may need to be excluded due to excessive motion. For example, eddy will tell you what percentage of slices were replaced and how much motion there was in each direction. This will allow you to make informed decisions on whether some data may need to be excluded. Once we have preprocessed the diffusion data, next we need to generate a connectome or tractogram. For this, we will use an approach referred to as multi-shell multi-tissue constraint spherical deconvolution. There's obviously a lot to unpack there, so let's start with constraint spherical deconvolution. Each white matter tractogram generally consists of millions of streamlines that pass through the brain and hopefully represent a model of what the actual white matter fibers of the brain may look like. In order to draw these streamlines, we need to understand what the diffusion looks like in each voxel of the brain, so that we know how streamlines might travel through the voxel. In the classical approach, which is called diffusion tensor imaging, we would describe the diffusion in a voxel as a single tensor. The tensor gives us the strength and the mean direction of the diffusion in each voxel. However, most voxels will be traversed by fibers that go in different directions, and the tensor model does not capture crossing fibers well, as it only gives us one direction per voxel. Constraint spherical deconvolution is a more sophisticated approach where we decompose the diffusion signal into a number of individual fiber orientations or FODs. Thereby, we are better able to deal with crossing fiber regions and to trace more accurate streamlines to the brain. Importantly, in order to better match biology, we want our streamlines to be limited to the white matter. Hence, in multi-shell multi-tissue constraint spherical deconvolution, we generate FODs separately for the white matter, the gray matter, and the CSF. However, in order to do this, we need an automatic way to distinguish between these tissue types and draw boundaries between them. And this leads us to the second issue related to infant data, which is that the white matter of infants contains very little myelin, which makes it difficult to distinguish between the white and the gray matter. So what do you think? In a T1 weighted image of a newborn, what is brighter? A, the white matter, B, the gray matter, or C, gray and white matter are equally bright? All right, I hope you had a chance to pick your answer. In contrast to what you would expect for adults, in newborns, it is actually the gray matter that is the brightest. So as you can see here, in a T1 weighted image of a 2-week-old, the white matter is actually darker than the gray matter. This is because the white matter of newborns has very little myelin. And as the myelin content increases during the first year of life, the gray-white matter contrast slowly shifts, so that by 12 months, the white matter is lighter than the gray matter. This is an issue for us because in order to fit separate FODs for the gray and the white matter, we need to know where the boundary is between these tissue types. In adult diffusion-weighted imaging, we often use a cutoff in FA to determine what is white matter and what is gray matter. As in adults, the highly myelinated white matter has a higher FA than the gray matter. However, since the white matter in infants is split in myelin, there's also no big difference in FA between the gray and the white matter. So this approach won't work very well. So for example, here's an image where white matter, gray matter, and CSF were separated automatically based solely on the diffusion data. As you can see in this adult example, the underlying algorithm does a great job at distinguishing the different tissue types in adult data. However, when we apply the same approach to infant data, it does not work very well. In this case, a substantial amount of white matter is labeled as gray matter. If we were to proceed with this, we would end up with a tractogram that has streamlines only in the small blue areas, which is obviously not what we want. One way to deal with this is to lower the FA threshold for what should be considered white matter, as this will get more white matter labeled as such. However, because there are places where the FA and white and gray matter are indistinguishable in infants, this will never get us all the way there. Moreover, because the white matter is developing so quickly, FA also changes rapidly in infants, and we would need to find a new FA threshold for each age group. Hence, what I would suggest is to not even try to generate separate FODs for the white and the gray matter. Instead, we can treat everything that is not CSF as white matter, which is now in green, and only separate between white and gray matter at a later step. What we end up with if we do that are nice FODs for each white matter voxel in the brain. This will allow us to trace streamlines through the entire white matter. We're not quite there yet though, because we have not yet separated out the gray matter. So our streamlines will go all the way into the gray matter, which has not much biology and it's not what we want. To overcome this, we can leverage an approach referred to as anatomically constrained tractography. For anatomically constrained tractography, we need to also collect an anatomical image of our infants, in addition to our diffusion-weighted data. In infants, this would typically be a T2-weighted image. We can then use automatic approaches like IBEAT or infant free server to identify the gray-white matter boundary in this anatomical image. Provided that the anatomical image and our diffusion data align to each other, we can then use this boundary to inform our tractography. Specifically, we can use it to ensure that our streamlines start and end at the boundary between the gray and white matter and do not enter the gray matter. This then ultimately results in a nice connectome for our infant data. Now that we have such a nice connectome, the next step is to identify the white matter bundles within the connectome. Here we run into our last infant-specific challenge though, which is that infants have much smaller brains than adults do. Just as a reminder, in order to perform tractometry on any kind of data, first we need to identify the white matter bundles of the brain. We can do so manually by basically chopping away at the connectome until we have the bundle we're interested in. This, however, takes a very long time. For me personally, it takes at least an hour per bundle, so I would not want to do this for a lot of bundles or large data sets. Moreover, identifying bundles manually will limit the reproducibility of the results. Hence, it's generally advisable to use automatic tools for this. And there's many different automatic tools out there for you to choose from. I'm listing some of them here in the teal box. It's important to note that these tools are generally developed using adult data, though. The tool that I'm going to focus on today is AFQ, or Automated Fiber Quantification. AFQ was originally developed by Jason Yeatman and is nowadays available both for MATLAB and Python. In order to automatically identify white matter bundles, every AFQ leverages two waypoint arrays for each bundle. A streamline becomes a candidate for the bundle if it passes through both waypoints. There can be situations, though, where a streamline passes through the waypoints for two different bundles, and AFQ solves such issues by also using a probability map for each bundle. The streamline will be assigned to the bundle that it overlaps with most strongly, so that each streamline is only assigned to a single bundle. After that, the resulting bundle is cleaned. Sometimes it is clipped to in between the waypoint arrays, and then its microstructural properties are quantified. Many of these steps will work just the same for infant data. However, there's one issue, and that is that the waypoint arrays and the fiber probability maps are defined in a commonly used adult template brain, the MNI brain. In a typical adult pipeline, the individual subject data is aligned to the MNI brain, and the inverse of that alignment is used to bring the waypoint RIs and the probability map into individual subject space. However, an infant brain and an adult brain are quite different, and the biggest difference is probably the brain size. So this leads me to my next quiz question, which is, the total brain volume of infants younger than 1 month is about 70% of adult volume, 36% of adult volume, 55% of adult volume, or 82% of adult volume. The correct answer here is 36% of adult volume, which I hope emphasizes how small infant brains really are. Here you can see a B0 image of one of our newborn participants. If we were to use AFQ as is, we would align this B0 to the adult MNI brain, which looks like this. Given that both of these images are at the same scale, this looks like a very difficult alignment to make, and maybe this is not a very good idea. A much better way to go is to align this B0 to an infant template, as this is a much easier alignment to make. For example, you might align it to the University of North Carolina neonate template, which is a baby template built from 94 typical newborns. This will require much less stretching of the individual infant data and will lead to a better alignment. From my experience, an even better alignment can be achieved if you first align the B0 to the same individual T2-weighted image, and then align the T2-weighted image to the template. This is because the T2-weighted image generally has a better contrast and resolution, which makes it easier to align. This last step is probably optional, though. So now you might wonder if this improvement in alignment actually has an impact on the bundles that you can identify. One way to test this is to first define your bundles of interest manually in the individual infant's brain. As I mentioned before, this is very labor intensive, but it does not require any alignments and can hence be seen as a gold standard. Once we know how the bundle should look like, we can then compare the output of automatic approaches that either align to the MNI brain or to an infant-specific brain to this gold standard bundle. Here you see such a comparison for one example bundle, the forceps major, which is a bundle that connects the two hemispheres of the brain. As you can see in this example, using an infant template works much better for identifying the bundle than using an adult template. In fact, in this infant, you can't even find the bundle at all when trying to align to the MNI brain. There's now a new version of AFQ called Baby AFQ, which has this different alignment approach built in. Baby AFQ is available both for MATLAB and for Python. In this case, it seems pretty reasonable to conclude that Baby AFQ is doing a better job just by looking at the data. But we also wanted to quantify this somehow across multiple babies. To do this, we quantified the spatial overlap between the manual bundles and the one identified by baby and adult AFQ using a dice coefficient analysis. A dice coefficient of 1 would mean perfect overlap between the manual and the AFQ tracks, and a dice coefficient of 0 would mean no overlap. And as you can see, both for the forceps major and the forceps minor, baby AFQ is a higher dice coefficient, so it lines better with the manual tracks than classical AFQ, which emphasizes the importance of using infant-specific tools for infant tractometry. Baby AFQ also includes a few additional changes, such as changes to the waypoint RIs. These changes are again helpful for handling the much smaller infant brain size. For instance, many of the waypoint RIs in baby AFQ are more spatially restricted, which improved the identified bundles. As you can see here on this graph, overall, baby AFQ performs much better than the regular AFQ for almost all bundles when used in infants. And this is true regardless of whether you use the MATLAB or the Python implementation of baby AFQ. I hope this illustrates the importance of using infant-specific tools for infant bundle identification. And luckily, more and more of such tools are becoming available at the moment. So instead of baby AFQ, you could, for instance, also use Tractolina, which is an infant-specific implementation of Tracula. So now that we have nice bundles in infants, we can analyze and compare various microstructure properties along the lengths of the bundle. This last step does not require any infant-specific changes, because here we reassemble the data to a certain number of points along the bundle anyways, so we have moved out of the infant-specific brain space. And this is my last quiz question for today, which is, which tractometry steps are particularly challenging in infant data? Motion correction tractography and bundle profile generation, motion correction tractography and bundle profile generation, motion correction tractography and bundle identification, and eddy current correction tractography and bundle identification. And the correct answer in this case is the third one, motion correction, tractography, and bundle identification. So in conclusion, infant tractometry is a comparatively novel field with much to discover. Where it will be most successful, pipelines are specifically adjusted for the infant brain. Specific challenges that one should be aware of when doing tractometry in infants include motion, low myelin content in the white matter, and an overall smaller brain size. Thank you for your attention.